Recording it.
Hello, everyone. It's my pleasure to be here. I presented a few years ago, but for these few years, many things changed in computer science, so we have a lot of topics to discuss, and obviously the progress in AI and machine learning of our interest. And specifically, I will talk about how to identify and avoid quasi-explanations in AI in machine learning. For applications in data science, it's actually now became key issue. Can we really trust what explanations are? So I will talk about motivations, explanations of models, user view of models, decision trees and rules as a key components for the explanation, and visual knowledge discovery as a growing field for explanations and AI in general. Why do we need explanations of predictions? The answer is quite simple. We have a whole bunch of examples where predictions are wrong. Here we have ping pong balls. Another example with panda. And everybody has his or her own examples. So motivations would be today to talk for explanations of black box methods and models. Then for explainable AI methods and models in the first place. If we will be successful in explanations in the first place, so models are explainable from the beginning, we don't need quasi-explanations at all. And then how to spot and avoid quasi-explanations and reveal and test foreign assumptions in AI methods for the domain experts. Okay, everybody familiar with hallucinations in large language models? And you can see now activities from Anthropic, OpenAI, and Chinese company. Everybody wants to get interpretability for high-risk applications like healthcare, because that Chinese company actually started doctor-free AI clinic, while doctors are skeptical, but still they claim very low error rate. So why do we use black box machine learning models without explanations? Cynthia Rudin from Yale University did a very good explanation for this. I just want to quote her. And unfortunately, while she told this in 2018, today is 2025, it's still valid. So it's exponentially harder to build transparent, explainable algorithm from scratch than repurpose existing black box deep learning algorithm to look at, say, medical data. Therefore, most researchers let algorithms run, and they try to understand later how it came to the conclusion. So, in short, it's much easier to repurpose than to build. Unfortunately, it's continued because if you take a look what NSF and NIH actually funding, unfortunately, they do not focus on building transparent, explainable models and algorithms in the first place. I witnessed it attending recently 3 panels at both NSF and NIH. So let me give one example. OncoScape for cancer research. The goal of this tool is visualization and analyzing genomic and clinical data. It's cluster genomic and clinical data and visualize them with idea that classes will be produced of similar cases, and respectively similarity can help in research better cancer diagnostics and treatment. And they use very popular classical methods, probably which you learned, all of them. Principal component analysis, multidimensional scaling, UMAP, and TSNA. And of course, OncoScape from Fred Hutchison, it's not unique. Many healthcare paper software systems, like I mentioned, NSF and NIH studies use them. Now we need to take a look what has actually happened with TSNA and UMAP challenges. First of all, base paper on TSNA has almost 100,000 other papers referenced it. But you can see here what is written. Despite popularities of these methods, cautionary messages have been raised against using both TSNA and UMAP embeddings to infer cell clusters distances. This is evidence from Harvard Institute of Advanced Studies. Similarly, critique about statistical understanding very limited from Department of Statistics here at UW. And the third one, identifying when TSNA meaningful and how they should be interpreted, open questions and practical, Department of Math. But unfortunately, what's happened in practice, you're probably well aware, because software is easily available, including this OncoScape. People use them and then and if something went wrong, they really don't know why. But so what is suggestion how we can approach this situation? I suggest a kind of written it in the 5 steps. Step 1, make assumptions of method clear for the users in understandable language without foreign terms for biomedical or any other users in their domain. Second, help users to verify assumptions. Third one, help users to use methods. Basically, it is not, as you see, just teach people how to run software. It's completely much more. Warn users of the risk of using methods that are not verified by these users. And finally, help users to find and use other methods if assumptions are not acceptable or use foreign terms for them. Like I already mentioned, situation is not quite good. Often warnings are ignored, not addressed, or even people may not know. Because if I ask you how many of you know about these challenges, probably not many. So, but obviously people in the domain would be happy to help domain experts to work on these steps if request would be there. Now I want to go a little bit to the history. As you know, John McCarthy introduced term AI in 1956. In 2006 was a conference at Stanford where he worked, and I attended that conference. And we had a session called "What's Wrong Went Wrong with AI." And obviously, everybody were interested to know what John will tell. He told very simply, 50 years are too short. Much more time is needed. But as you know, that old AI actually was explanation-based, with logic-based. And he even told about the bad ideas, and neural networks was listed in the bad ideas. And it was few years before renaissance of neural networks with deep learning and great success now. Okay, in 2009, in another conference, another leading figure in machine learning told that only unsuccessful people request explanations, because that time really people wanted accuracy, because accuracy was not there. Finally, when accuracy reached appropriate level in the majority of the important tasks which were not successfully solved before, DARPA started a program, Explainable AI, and coined that abbreviation, XAI. But now, if you take a close look what DARPA actually wanted in 2016, they wanted models which will be explainable from the beginning. But most of the 10 years spent really trying to explain black boxes and not much built from scratch explainable models. Okay, so where do we really need explanations? Mostly we need for high-risk tasks. If task is not high risk and has high accuracy, nobody really need them significantly better than they can be provided. And now you see long list of the high-risk tasks. So I just want to summarize where challenges are. Low-quality explanations prevent domain experts from trusting and deploying models in high-stakes domain, like medicine and many others. Explanations suitable for data scientists to debug and improve accuracy are not the same what lead to domain expert to confidently risk deploying models in critical applications. So they really take risks. And if you work in particular domain, you are those who need to take risks, not computer scientists who will help you to build more accurate models. Okay. Popular explanations often generate quasi-explanation that fail to meet domain expert needs. And I will give examples what I meant. Okay, and it's also, like I already mentioned, explanations bring foreign assumptions to the domain on the top of foreign assumptions which predictive method brought themselves. So it's a double assumption. So you are in really difficult position to decipher those assumptions. And the problem is that many assumptions are hidden and are not known, not necessarily even known to the authors of the methods. So what I'm suggesting, really, I'm advocating for explicitly revealing assumptions of machine learning models and explanations. So the domain experts can critically assess their validity. So when somebody offers you methods, you need to ask, what assumptions are, how can I check them? That would be desirable work on your side if you're from science domains, not computer science yourself. Okay. And I will present some methods which free from foreign assumptions. And this is what I, in the area of visual knowledge discovery, because. So now I want to summarize where we are now in short. Black box predictive models dominate. I would be happy if somebody would debate it with me and tell me that it's different. Next, high demand to explain black box models is present. That's very good. You have seen a quote from Anthropic and many others. Prevailing explanations method weak for domain experts in high stakes domain. Often quasi-explanations are offered and confuse users as a real explanation. And high demand for strong explanations still absent. And high demand for explainable model in the first place. So to avoid all this above, still absent. So now we go to really details. So first I want to define what is actually explainable AI and machine learning. It is different that you can find in some sources. Let me read. Explainable AI ML is much more than allowing humans to understand why certain decisions are made in the terms of algorithms, but also allowing to match this understanding with user domain knowledge in domain terms. So when we wrote this, what is in the black here, it immediately means that it requires human in the loop. So you see, explanation model fundamentally cannot be done by testing accuracy. It's required that the user accept it. So it is going beyond traditional pure computer science. Okay, so a little bit about terminology which are commonly used: black box and white box. In the black box, we simply don't have explanation which is acceptable for domain expert. It can exist explanation which is acceptable for computer scientists to debug and improve model. White box actually has both, but not necessary that those explanations good or they can be good or bad for domain expert. I listed here decision tree and regression models. You can often find in the literature linear and regression models as a white box were explained. I will be cautious and put some explanations later why I need to be cautious. Okay, so what we need to explain? Basically everything. Features, algorithms, models, parameters, and models as a whole. And we have limitations on the human side. We cannot consider very complex explanations simply due to our memory limitation, limited knowledge, domain knowledge, and often domain knowledge is not formalized. And explanation granularity, which we can really accommodate. Okay, obviously, the explanation of the right hardly can be called explanation. So, people want natural language, easy to understand. Again, ideally, it should be in the terms of domain ontology. But often in many domains, we don't have a formalized ontology, so that's really very difficult issue. So it's not accidental that large language models try to fill the gaps here, because indirectly they present domain ontology. So now I want to characterize what type of explanations we actually have. The first one, it's describing importance of the features. Let's say age, BMI, blood pressure, and sex. You can order which one is more important, which is less important in the black box. If a user agrees with this, then you can say it's a partial explanation. Nobody can call it full explanation, but at least often people use it as a sanity check. If the order of explanations provided by explanation method completely contradict what domain experts believe are true, then it means both need to be revised. Original prediction method and explanation method. Then we go to models in understandable form, like you see here as a logical rules. Medical people can understand them without learning or going to this class. That's sufficient for them just to read it. Okay. And simplified models, which is approximation of the black box. So basically, in both situations, we use this logical models. Another method is similar cases. You simply have, let's say, case 2.34.9. You show similar case in red and tell that it's from class 1. Or you show class which is far away and tell it from class 2. And this can convince you. Often this works very well under one caveat. The similarity of cases often computed in a way which is not interpretable itself. So you need really to ask how people, algorithm actually did it. Okay. Now, there is actually finally formal definitions from Muggleton, from Cambridge. Of course, I don't have time to talk in detail, but main idea of his concept of definition of comprehensibility is that human who learned explanation and model should be able, without any further sight, to be able to classify new cases. So, and he actually conducted some experiments telling that it's doable. And also he measured inspection time and complexity of the model which human analyzed. So it means it's becoming more experimental science than pure computational computer science. So And then people continue to formulate the idea of simplicity, explain it like I am 5 years old, and ready to sacrifice or de-emphasize accuracy to get explanation that people can understand. And of course, role-based explanation for us and explanations for doctors can be quite different. Okay, then very important explicit and implicit explanations, especially for images, they are popular, implicit explanations. So people simply show you highlight pixels where supposed object of interest is located, but it does not tell what is it building or what it is and what specific type of building. So you as a human compare original image and that explanation will tell, yes, it looks reasonable. And explicit, when somebody exactly answer your question, what type of building and where it is located in the image. Okay, so now I provide multiple ways how explanation looks like. So it can be actually images representing multidimensional data in the different form. I will talk about this later if time will allow. And obviously, why people like visual understanding? Because we can analyze it in parallel. It's much easier than textual or understand algorithm description. Now I will talk about user view on models and their explanations. So first, we have two fundamentally different approaches. Approach one, we build accurate explainable model from the very beginning, like decision tree, logical rules, sometimes linear models, but I put question mark again, I will explain why. And more typical today, we built black box, then we built explanation model, and together they provide explainable model or quasi-explainable model. And the first one called internally interpretable and the second one called externally interpretable. So what's the problem with externally interpretable? You only simulate behavior of the model, but you are not really explaining what the model is doing inside. So you basically approximate it. And as every approximation, you have no guarantee that with a new case, it will behave in the same way as an explanation model tells us. Okay. Now we finally come to the assumptions. We start with the basic assumptions of feature space and training data for user to verify. Okay. I consider very popular example iris data. Probably all of you run this data one way or another. So what we see on the first row, how those flowers are actually looks like. And the second, in the middle, linguistic description. What's the first class, Cytosin? Small length and small width. And Virginica, large length and medium and large width of petal. Then you can take a look how linear model actually classified these cases. You see at the bottom, yellow, it's a Cytosin class, and in the middle, versicolor and Virginica at the top. And you can see red points, which I put there. I can ask you, are these real cases or not? What do you think? Can you find flowers with these properties? I'm not sure biologists are there, but most likely the answer is negative because it doesn't satisfy intuitive requirements, small length and small width, because length is very high. If you see the bottom point here, so here. If you see my mouse is not there, you cannot see. Okay, so what it means? Well, we can convert this example to the assumptions. So assumption is that every point in the space is a legitimate case of the classes. But this assumption is foreign for the iris data. Only actually cases close by to those are representative to real flowers. On the figure on the right, we actually built alternative visualization and modeling with linear. So the cases only which are in the circles in that category. So we actually request to build a model which will not make assumptions which are not appropriate for the data. So in general, we can formulate this example as a more formalized assumptions of a feature space. All points of the feature space are legitimate cases of the classes. And another assumption about training data. Training data represent all legitimate cases of the classes. So what it means? That all points in the feature space that are close to training data are legitimate cases, and all outside really not. You obviously can answer this question. Most likely you will tell, no, I'm not sure that my training data are sufficient, but I don't know how far. So it means these assumptions, at least if you know that they exist, and if you cannot justify for your task, do not be surprised that the model will not work as you expected. So, but by the way, often these two assumptions simply contradict to each other. Okay. Now, example of black box explanations with assumptions to be verified. Okay. This is a SHAP3 explainer. Probably many of you already have seen it. So what it is doing, like I already mentioned, we have a black box model, and you have a patient with age 65, BMI 40, blood pressure 180, and she's a female. And black box model output the cure mortality risk score 4, which is quite high. Okay, and explanation on the right give us idea. And you can see here contribution to this mortality score 4 from age is 2.5, from BMI 0.5, from blood pressure 3, and from female it's actually -2, because for female actually it is less common than for general population. Okay, now let's try to analyze what kind of assumptions this model actually made. Because typically what I've seen many times when I need to review papers sent for publications, people use software which is publicly available to type this type of output and present it as an explanation. In the best case, they ask the main expert if they agree, otherwise they will discard the model. Now let's try to analyze a little bit more. You can see in this table that blood pressure has a score 3, but BMI has a score 0.5. So BMI here, 6 times smaller score than blood pressure. So basically it means if you are a physician and you want to decide what you will do, then you will pay much more attention to low blood pressure to the patient than BMI. But medical sources tell us obesity is responsible for approximately 65-78% of hypertension cases. So here, actually, BMI, this lady is definitely heavily obese. So most likely, her obesity is a cause of the blood pressure. So the treatment really needs to be first about BMI rather than blood pressure. So now you can see what is the issue. So if you're able to discover such inconsistency, you of course start to ask, please explain how did you derive. But at the first glance, if you don't pay detailed attention, you would agree with this, so you would not ask explanation. So it is that you need to ask explanation even when result seems reasonable for you. That's the main message. Okay, now let's try to analyze how it's happened. Can we actually accept those assumptions? First assumption, the model behind it came from the cooperative game in economics, known as a Shapley Balance. Shapley is a very respected person. He got Nobel Prize in economics. But the ideas in economics and ideas in machine learning not necessarily the same. So you need to check that what you can use in cooperative game, it's also applicable to machine learning. You cannot mechanically just tell it was approved in economics, now I will use it in machine learning. You need to check it. Okay, and now let's a little bit analyze that situation. In economics, we can have soccer players who need to split money which they get for winning the game. Let's say $1 to one player, $3 to another player, and so on. So there is no doubt that we can split total dollar amount between players like this. But splitting mortality risk between such heterogeneous data, it is not intuitively clear. Behind of it, a lot of math stand, which not easy to decipher. Actually, I can go to next page, where it's a one page of analysis of those assumptions in mathematical terms. This is another page. Of course, if I will just analyze what I wrote here, we will spend all remaining time. So we will not do this, but we will ask ourselves, what is the chance that clinician can confirm or reject assumptions in that mathematical form? Most likely they will not be able to do this. So it means we have following alternatives. You already have seen this assumption. Request assumptions of the explanation black box models in understandable form. Another, request explanation that are free from assumptions. Request prediction model that are not black boxes at all. Obviously, I advocate with the second and third, because as you have seen, really present explanations in the easy understandable form for people who never touched all this deep math needed behind. It's not realistic. Only for the simple assumptions it can be really done. Or I would be happy to see if it can happen. But the major problem with the options 2 and 3 is that we need to get competitive accuracy with black box models, because black box neural networks in deep learning models actually demonstrated high accuracy. Now more and more works, including my team works, demonstrate that we can build models with competitive accuracies. So when it will be reached, hopefully, situation will be much better. And another way I want to emphasize impact of visual knowledge discovery, because visually it's a way to decrease need in go to deep mathematics for domain expert to understand if assumptions and the logic of the model are acceptable. Basically, participate in direct building a model, trustable model. Okay, now I will talk about linear models. Okay, we still have a little bit time. Okay, what's the logic of using linear models as explanations? You have a black box model. You build local linear model, like in that picture, you have a complex nonlinear model. You interpolate it with 3 linear models, and local model looks like this. And then you extract from local linear model logical rules, which actually people can understand. So basically, linear models often require 2 steps. Even in the literature, you find that people say linear model is sufficient. It is not the case. The test is very simple. Try to go to doctor and give him or her linear model and ask to be comfortable. If you will be successful, great. But most likely you would need to go to give him or her logical model. Okay. This is the implementation of that idea with 3 steps in our work, where you have seen on the top linear model of cancer and benign cases, and in the middle you have benign cases, in the end you have malignant cases, and those blocks correspond to local linear models. Later on, if we will have time, I explain details. So I want to summarize what's the issue with linear models. If we ask chemists if 3 molecules and 30 degrees Celsius temperature in chemistry, can we add these 2 very different things, or 3 kilograms and 5 meters? Physicists, obviously, they will tell you that there is no meaning of this one. Of course, weighted sums with these kilograms and meters, molecules and degrees have no meaning. But in machine learning, what we do, we all the time sum up heterogeneous numbers like 0.2 x1 plus 0.6 x2. We hide the heterogeneity, and traditionally in mass, assumption was that all these attributes have the same meaning, let's say pixel intensity. Perfect, no problem. You can operate with this. But in the medical domain or other domain with heterogeneous data, it creates a problem. Okay, so now I hope that I will be able to explain a little bit technical things. So what is the idea? When we want to see a linear model and to be able to judge how it works beyond the formulas which I just shown to you, the idea is the following. Let's first assume that we have a 4-dimensional number, 4 digits, 0.8, 1.2, 1, and 1.8 on the left and in the bottom. Of course, because it's a 4-dimensional point, we cannot visualize it in 2-dimensional space. We live in 3D space, yes? So how we will do this? We create 4 coordinates. Coordinate x1. Sorry. So this is the coordinate x1, coordinate x2, x3, x4. So we do not connect them like the standard Cartesian coordinate. And pointing, we put on the first coordinate. It's a blue there. 1.2 and the second one again is a blue vector. Then 1 is a blue vector here, and 0.8 is a blue vector here. So basically, we represent them. This 4-dimensional point is there. Then we move vector x2 to the end of x1, x3 to the end of x2, and x4 to the end of x4. Okay, so we get a polyline. And then we project the polyline down. And then we can prove mathematical simple statement that basically the point down corresponds to linear combination of this vector with the coefficient that proportional to those angles. So now what it means, if you take not only one this point, but multiple points, you can draw several lines. Let's assume that this is the cases of one class. At the bottom, symmetrically, you will draw cases of another class and you project them. So if you are so smart, so you correctly selected those angles, you will be able to get cases of the one class on the left and cases on the other class on the right. Okay, and now you see actual cancer data. On the top, you see benign case. On the bottom, you see the malignant cases. And you can see that the green line actually is where the crossing between them. So only 2 malignant cases are in the benign. So this classification is different to the confusion. Okay, and yellow two lines show where they overlap. So now, you, as a, let's say, cancer professional, now you tell me, or just not me, yourself, that you don't happy that two malignant cases classified as a benign. You tell, okay, interactively we simply move green line here, and this to where the yellow line is located. And then you got zero misclassified malignant cases. But of course, the price will be tremendous number of benign cases now will be recognized as a malignant. But that's the price if you want to sell. So now the main expert can be in the driver's seat of the really developing model, does not need somebody other. And also, the angles of the attribute really tells how important they are. So this is a demonstration what can be done. And we call it general line coordinates because in traditional coordinates, all coordinates should be vertical and orthogonal. Now you can see, and of course, this is a really non-dimensional data. And we have an experiment successful with 400-dimensional data in this way. Okay, now how the same idea used for principal component analysis. So what's the typical problem with principal component analysis? They're extremely popular in data science and in machine learning. First of all, to decrease dimensions and to visualize data. But the problem is, it's extremely difficult to interpret what actually principal component means when you want not just to show nice picture. So what we do, on the left, the plot shows you data in the first two principal components. But in the bottom here, this principal component explained through the original attributes, because each principal component is a linear combination of original attributes. And similar, on the left, you see the figure for the second principal component. So what it means, you click particular point in parallel cut in this plot of principal components, and yellow line shows you how actual interpreting explain you what it means, this principal component. On the right, similar for the third and fourth principal component. And you can continue this. Basically, this is an explanation which I already gave you. Most significant variables are captured. So it means you can now explore this data if principal component is meaningful or not for your task. Okay. Of course, I don't have time to talk about algorithm, how it is doing. Okay, this is a more detailed description for 10-dimensional data. So because time is limited, I will show you on one extra example. For decision trees, another very popular method for explaining machine learning algorithm. Basically, today we have a really only decision trees and linear models, logical rules, which people do not debate that they're explaining. So on the left, you see traditional decision tree, and if I have a particular case, you can trace it and to tell, yeah, that's malignant case. But it does not tell you how close or how far this case from the breakpoints which are there. So what we did, we actually used those lines to represent attribute. So now you can see at the top here, the first attribute you see. Actually, it has values from 1 to 10. So the breakpoint is 2.5. So it means we have an actual case with a little bit above 2.5. And you can see with this attribute, and it's dotted line. Then you go to the second one, it's again dotted line. So you can trace all these dotted lines and see how risky or how reliable a solution for this case. So for dotted and for solid line, you can see difference. So you have a chance to analyze yourself. You don't need to play formal. So basically what it means, this is an implementation software. So we bend attribute to make it edges of the tree. That's the idea. Okay, another method which I want to emphasize for remaining time, okay, this is let me explain the idea of this method. You see here, standard description of the decision tree with all its logical products. So we pick up one line and try to visualize that line in the first rectangle. So first attribute is the cell type horizontal and the nucleate is a vertical. So this property less than 2.5 and less than 4.5, it's a red rectangle on the left. And it's actually 100% of cases are benign here. But on the top of this coordinate, only few out of 6 cases are from the opposite class. And the other is gray. Then we go to another line, and then we pick up another pair. And for them, again, mark green and red and areas. Then we go to the short, basically passing this decision tree. And finally, get this description. So now you can see, you can trace any case multidimensional and see all details. Okay, so this is a kind of toy example. This is a real example with much more data, with interactive abilities to start from this one and coming to a very clear description. So you can analyze the decision tree. If this decision tree approximates you the black box, so now you can understand how the decisions actually can be made. And of course, you can modify this tree. And advantage of this is that you can side by side draw 2 pictures. One where you have a training data and another where you have testing data, and you can see how testing data are represented in training. So you can see if the training data were sufficient or might be need to be improved. And again, it does not require computer scientist. The domain expert can do this himself or herself. Okay, because I practically used all my time. So a few words about the future. Basically, we need to develop methodology, computational methods, human in the loop, and visual knowledge discovery as our focus. That's basically it. And of course, if we need to talk about all of this, it will be 10 lectures again. That's it.
As you share your results with us, because I know that many people here are writing papers and trying to explain their models. And I know we're at time, but if you have 1 or 2 questions for Dr. Kovalerchuk, asking now or maybe after the seminar. I have a question. I love the logical, but especially how do you have any recommendations for getting started or thinking from the start to build a SPC? Any like considerations for making sure we can get there?
Okay. So you mean something like this?
Yeah, like making sure we always build so we can provide this to our end users.
Basically, you have I need to clarify your position. If your position of computer scientists, it's one story. If your position of, let's say, biologists who want to use it, from the computer scientist, it is a very nice way to debug a model. So you immediately see if so many cases close to the edge, yes, so the model is risky. For biologists, it is the abilities to check if the model is inadequate, because you can see some light green or light red areas means that the confidence in that area is low. So they may actually tell, I will only use where we have the dark green and dark red, but for the other areas, I would prefer to build another more complex model. So that would be if I captured your question.
I was just wondering if your software is available.
Yeah. Okay. Yeah. That's. Let me. Okay. Let me. Yeah. That's basically this is the GitHub CW Visual Knowledge Discovery Lab in GitHub. Yeah, and of course you can contact me, and so that's.
Well, if you give us the link, I will pass it to an email to everybody.
Okay.
Do we need to compile them from each computer?
No, it's already fully cooked, so
Okay.
just.
Thank you. Thank you so much.
Okay. Mm-hmm. Thank you for.
Great. I have a question. So I see a lot of like red lines and blue lines in the chart, right? When people are contributing their research. And I always wondered if that's the way to prove, like all the predictors should be there, or the sharp analysis tells you to reduce maybe this, yeah, and remove it.
Yeah. So you read. So my main point is do not just trust software itself.
Yes.
That's the key point.
Yeah.
Yeah. Why? Why they suggest to do.
Thank you so much.
Yeah.
Thank you so much for the brilliant talk. It's like, mine's just as a simple question because I'm not part of the computer science community. So the main idea of building of explainable AI and artificial intelligence is like we're using some structures with some models with a like rather clear or simpler structures and apply some skill to make it precise to maintain explainability. Is that a key point?
If I correctly captured, so basically there are two approaches. One approach in physics, they really built meaningful physics models. What we do in machine learning, we really build empirical models based on the data only. So if you have knowledge in the domain, then in the classical AI, which was coming from the time of McCarthy, people actually able to record knowledge from the domain as axioms and then do logical reasoning with them. And like I mentioned, Michaelton and the other groups and our groups, this is a way how you can naturally do this. But typically, unfortunately, it is not well represented in cooked software. You most likely will be in the position significantly work yourself.
Oh, I see.
If I captured your question.
Yeah, of course. Thank you so much.
Okay. If I captured your question.
Well, I did that right now.